Hello everybody, this starts our third day of notes in section 5.3 on logarithm properties, our start to logs. But before we get into our day 3 notes, I'm actually going to go over a homework question that I am sure you guys had so much fun with, so that's why I'm actually writing 5.3 day 2, because this is going to be a 5.3 day 2 homework question before we get into the 5.3 day 3 notes. And we are going to talk about, drum roll please, number 6. And number 6 says log base d of the fourth root of 16 x squared y, all divided by w to the third, z to the eighth. So if you did not need help on this question, feel free to move the bar forward a little bit and check your answer. If you did need help, please look at what you did for number 6 and then maybe take out a blank piece of paper or do this one on the back with me if you had some struggles. Now the key here is to realize that our properties, our 3 toolbox properties, haven't changed. And since we are going to be expanding this, we're going to look to see if we can use power property, quotient property, or the product property. These are our 3 tools in the toolbox. So to get started, let's first remember that when I see a big fourth root like that, I can actually write that as, so let me get my line going here to keep it nice and neat, log base d. How can I write that fourth root as an exponent? Well, just like square root means raised to the 1/2, fourth root means that this whole fraction is actually being raised to the 1/4 power. There are 2 options, 2 choices. Option 1, send in 1/4 to every term inside parentheses. Or option 2, use the power property. So what I mean by that is remember your exponent properties, that this 1/4, I could send it to the 16, and I could send it to the x squared, and to y, and to w to the third, and z to the eighth, and go from there. For these notes, I plan on using option 2, the power property. So this power can be brought down and become the coefficient of this log term. So it'll be 1/4 times log base d of that fraction, 16 x squared y, all divided by w to the third, z to the eighth. Now there's many ways to get to the same answer. So if you did it a different way, no problem. We'll see if we get to the same answer, and that will be the way that you'll know if your method was correct. So I've taken care of that exponent, which is nice, and now I have log of a fraction, and we know that from our properties, division is tied to the quotient property, and division becomes subtraction. So this is going to be 1/4, and now I'm going to start using some big brackets, because it's going to be 1/4 times whatever we end up expanding here. So log base d of the numerator, which is 16 x squared y, minus log base d of the denominator. Close my bracket. Brackets are a great way of distinguishing like a big set of parentheses. Instead of having to do big parentheses, as soon as I draw a bracket, they stand out. So I've used my quotient property. What can I use next? 1/4 is still out here. Get my bracket going. Well, inside this argument, this is log base d of 16x squared y. This is a product, so I can apply the product property here and here. So let's see what that's going to look like. It's going to be log base d of 16 plus log base d of x squared plus log base d of y. So we have finished expanding this piece using the product property, and if you're using colors, I'm going to be using green to kind of show that this came from this. And now we need to take care of using the product property one more time over here. But remember, when we're subtracting, I'm going to have to use parentheses because we're going to have to send in that negative to whatever we end up expanding right here. So let me switch colors. I'm now expanding this piece right here. So that will be, in parentheses, log base d of w cubed plus log base d of z to the 8th. And now I'll close my bracket. So I just expanded that into this. From here, we're really using our algebra skills and maybe one more property, we'll see. 1/4 is still on the outside. Log base d of 16, nothing I can do with that right now. How about log base d of x squared? Well, as soon as I see that I have this exponent, I'm like, ooh, I can use my power property. That's going to come out front and become a coefficient, so that becomes plus 2 log base d of x. And there's no exponent here, so that will stay, plus log base d of y. If you notice, I'm putting all of my arguments in parentheses because it just helps me to remember that that's what they are. But you technically don't have to use the parentheses there. Like I wouldn't have to have y in parentheses. I'm going to consider if I can use any properties and distribute this negative at the same time. So this is going to be minus, and then I see w cubed, so this 3 can come out front. So that'll be minus 3 log base d of w minus, so we're sending in the negative, and this 8 can come down front. So minus 8 log base d of z. Close my bracket. If I look here in terms of expanding, there's no other properties I can use, so my next step is going to be to send in 1/4. And when I say send in 1/4, I'm saying that we're going to be distributing it to the coefficients of the logs. Notice I'm being very careful where I draw these arrows. I don't want to keep going, but it's going to be in front. We're going to be multiplying the coefficients by 1/4, not the arguments. You can't touch that. So what I mean by that is that this is going to become 1/4 log base d of 16. Notice, we did not touch the argument. Plus 1/4 times 2 is 1/2, and then log base d of x. Now sending 1/4 to this term, plus 1/4 log base d of y minus 1/4 times negative 3 would be minus 3/4 log base d of w. And then last but not least, 1/4 times 8. That becomes 8 divided by 4, which is 2 log base d of z. And we are 99.9% done. When the arguments are variables, so x, y, w, and z, there's nothing else I can do. But this guy right here technically I could do one more thing. Let me show you what that is. I'm going to put it in green. So if I actually use my power property, this becomes log base d of 16 to the 1/4. And I know that 16 to the 1/4 is 2. That comes from my chart knowledge. The 4th root of 16 is 2. So technically, this piece I could take one more step, and the final answer will be log base d of 2, and then the rest of this is the same. So I'm just going to bring it all down. Space is your friend. A lot of the key to success here is not crunching up the work in a couple lines. Give yourself room to write. And on any kind of assessment, if you saw that you could go farther, I would be fine if you actually just did this for me or circled that and said log base d of 2. If you're willing to rewrite this, that would be great too. But I understand that and be like, man, I have to write all that again. But yes, look. So this right here is our final answer. Those of you looking for a little challenge, remember that this was option 2 using the power property. So let me reset the question. Coming way back to this original. Looking for some takers on what option 1 would be, which was sending 1/4 in to every term. And go from there. So it'd be awesome if some people maybe take on that challenge and bring that into the next class. And we should get the exact same answer. Okay, so let's officially get into our 5.3 day 3 notes. So our title is going to be 5.3 function, 5.3 day 3. That's a bad 3. There we go. Day 3. Function composition. And finding inverses. Because exponential and logarithmic functions are inverses, we can verify using function composition. So let's look at our general form first. Our general log notation says g of x equals log base b of x. And let's say I had my general exponential equation here, or function. F of x equals b to the x. Let's see what happens when we do g of f of x. So again, I read that g of f of x. So bring back that prior knowledge. What are we going to be doing? What's going to get substituted into what? Well, when I say g of f of x, that's like saying g of 5. And if I said g of 5, I'm positive you'd say that you'd be plugging in 5. So with that same idea in mind, when we say g of f of x, we are going to be substituting f of x into g. So let's write g first. That'll be kind of like our guide function. Oops. G of x equals log base b of x is what we're starting with. And we are going to be now doing g of f of x. So that means wherever I see x, I'm going to be substituting in f of x as the input. If you have a highlighter, you might want to highlight that to make it stand out. Just for this first step. So that will be log base b. I see x right there. So now I'm going to be plugging in b to the x. Because again, f of x became the input. We have two options for what we see here. In our very first day of notes, we had a property that told us that log base b of b to the x will actually equal that power. If we forgot that, no worries, we can use our power property that says x can come to the front. So this equals x times log base b of b. And then we do need to remember that when the base and the argument are the same, log base b of b has to equal 1. So the result is x. Now let's see what happens if we do f of g of x. So we're starting with f of x equals b to the x, and now what are we going to be plugging in? F of g of x, so we will be plugging g into f. Our input is now g. So b to the, I see x right here, so that's going to be log base b of x. Now to understand where to go from here, we're going to take a little detour in our train of thought. So I'm going to be switching colors. If you have another color pen, you can switch colors with me, or maybe put it in a little box when we're done. We need to remember the general form log base b of x equals n. How can I connect that to exponential notation? So we're just taking a step back, taking a bigger picture view. Log base b of x equals n can be rewritten as b to the n equals x. Remember, circle the base, come around where the equal sign is, b to the n equals x. This is going to be very useful to us in a moment, because we're going to be using both definitions, both of these together, where if I look at this, this says log base b of x equals n. Well, I could also read it the other direction. N equals log base b of x. So right now I'm just going to literally write it the other way. Remember, equality goes both ways. So watch what happens when we use these two pieces that I put in boxes together. B to the n equals x. Oops, sorry. Didn't mean to write that. B to the n equals b to the log base b of x. Why was I able to write that? Why was I able to write that? Well, check it out. Right here, we said n equals log base b of x. So b to the n is the same as saying b to the log base b of x. So I use this right here because n equals that. But I know from here, remember these are all connected, what I just wrote here. I mean, this is practically this, just written the other direction. But b to the n is also equal to x, which means this has to equal x. So what we just did here is prove something very important. Let's write down what we just proved. We proved that g of f of x is equivalent to log base b of b to the x, which equaled x. And we proved f of g of x, so composition the other way, which was b to the log base b of x equaled x as well. We can use these facts to simplify. We're going to kind of, in air quotes, put an unofficial way of describing this as the canceling property of inverses. Sorry about that, guys. That was a very long bell. Canceling property of inverses, which will leave us with So let's take a step back and look at what we're going to be left with. When in the process of us doing what we did up here, when we got to log base b of b to the x, algebraically we proved to ourselves that that equals x. So whenever the base and the argument are the same, we are left with the exponent. Always. Starting with an exponent, instead, if I had b to the log base b of x, that also equals x, where that x, in terms of where it's located, is what you're taking the log of. Let's get to practicing. Once we start practicing, that's where this really comes into focus. So the directions are: use inverses to simplify. Number 1. 10 to the log of 2. Ten to the log of 2. This will equal 2. And my question is, why? Well, remember, when we just see the word log with no base, that's an invisible base 10. 10 to the log base 10 is the same as b to the log base b, where the base and the base of the log are equal. It means we're just going to be left with what you were taking the log of, which was 2. If you want to write that out for yourself, because what this really means is 10 to the log base 10 of 2. So 10 and log base 10 are inverse operations. They literally cancel themselves out, leaving us with 2. Number 2, log base 3 of 9 to the x. Log base 3 of 9 to the x. Well, at first glance, we'd be saying, like, I don't see anything. But then we have to remember our ability to rewrite. So how could I rewrite 9? I kind of have a vision of like a goal of 3. So let's see how that works. Can I write 9 as 3 to a power? And I'm hoping we're all saying like, yes, 9 is 3 squared. And x is still the exponent. So 3 squared to the x. Power over power, we multiply. So that will equal log base 3 of 3 to the 2x. All I do is multiply 2x. Now what happens with log base 3 of 3 to the 2x? Well, if I go back up to my general discovery we had up here, log base b of b to the x, these cancel each other out. Log base b and having an exponent of b to something, these right here are inverses of each other, leaving behind the exponent 2x. Another way of thinking about it, technically I could apply the power property, and that would become 2x times log base 3 of 3. From our very first day of notes, I know that that equals 1, leaving behind 2x. So it's not just disappearing. We didn't just miraculously go from here to here. What's really happening is this. But we're using our knowledge of our properties to not have to write this out. Number 3 says 7 to the log base 7 of x minus 6. Once again, 7 and log base 7 cancel, just leaving behind our exponent here, which is x minus 6. Number 4 says log base 20 of 8,000. I'll make sure it doesn't look like a decimal point. So let me rewrite that. Log base 20 of 8,000 to the 2x. Just like before, where it's not a direct connection yet, if I see log base 20, strategy would be, can I write 8,000 as 20 to a power that I don't know yet? So grab your graphing calculator if you haven't gotten it out yet, and you're trying to figure out 20 to what power is 8,000. Start small. 20 to the first is obviously 20, and go from there. Give you a couple seconds to try that out, or press pause and try it out. And I'm hoping that if you are continuing to listen, you figured out that I can rewrite 8,000 as 20 to the third. So 8,000 can be rewritten as 20 to the third, and 2x is still the power. So 20 to the third to the 2x. Applying power to a power, we will multiply, so this will become log base 20 of 20 to the 6x. Log base 20 of 20 cancels out, leaving behind our exponent, 6x. Now that we have started to experience these canceling properties of inverse operations in terms of logarithms and exponents being inverses of each other, and how that can be really helpful to us, as evidenced by what we were able to do with numbers 1 through 4, now let's actually talk about how to write the inverse function. So we have been using the inverse properties to solve or evaluate. Let's now learn how to write the inverse function. And we have experience writing inverses. So as I write this title, think back to when we were writing inverses for linear functions. So for example, you don't have to write this down, but if I gave you y equals 2x plus 8, what would you do to find the inverse? I'm hoping the first thought that comes to mind is switch x and y and solve, because that's exactly what we're going to write for our steps for inverses working with logs and exponentials. Step 1, switch x and y. Step 2, if we're going to go from an exponential to a logarithmic function, we will be taking the log of both sides and just make a note it has to be the same base. If we're going from logarithmic to exponential, we will raise both sides up. And again, same base. If you want to grab your highlighter, this should be one color. And this one is a second color of your choice. All right. Let's get to work. Oh, sorry. One more step. 3, solve for y. That one's important. I didn't like how my highlighter boxes looked, so I'm just going to take a second and change the color of the font so it looks different. But if you have your highlighters, that would be great for you guys to highlight these in 2 different colors, please. All right. Now let's get into it. Directions. Write the inverse function. Number 1 says y equals log base 3 of x. So step 1 says switch x and y. Let's do that. X equals log base 3 of y. Now, are we going exponential to logarithm, or are we going logarithm to exponential? To write the inverse, if we're starting with a log, we want to end up with the other form. So we are going from logarithm to exponential. Looking at the note we wrote, oops, didn't mean to move that box. Going from logarithm to exponential, raise both sides up, and it has to be the same base. So if I see log base 3, I am going to do 3 to the x equals 3 to the log base 3 of y. We just raised both sides up using the same base, and in this case, that same base is 3. Now that we've done that, we are told to solve for y. So let's see. 3 to the x is going to stay. But now what happens? Using the inverse properties that log and exponentials have, what happens with 3 to the log base 3 of y? Well, I know that 3 to the log base 3 cancels, and it leaves me y. Directions said solve for y. In this case, we're done. So my inverse function is y equals 3 to the x. Number 2. Y equals log base 1/4 of x plus 3. Step 1. Switch x and y. X equals log base 1/4 of y plus 3. Once again, we have to ask ourselves, where are we starting? Where are we going to end up? Well, I'm starting with a logarithmic function, so I want to end up with a exponential. But before I can before I can raise up to the same base, we need to isolate log term first. So that means that we need to subtract 3 from both sides. I'll have x minus 3 equals log base 1/4 of x. Now that the log term is by itself, isolated, now we can go same base. Well, I'm trying to be strategic. I mean, technically you could choose any number as a base, but if I'm going to be strategic, I will choose 1/4 as my base. Because I know that if I do that, oops, typo, should be a y. Sorry about that. Log base 1/4 of y. I know that if I do that, I'm going to be in good shape because my directions are to solve for y. Y right now is locked up there in that exponent spot, but not for long, because 1/4 raised to the log base 1/4 cancels. Those are inverse operations, which means on this side, this will stay, 1/4 to the x minus 3. But 1/4, like I just said, 1/4 to the log base 1/4 cancels, leaving behind y. Direction said solve for y. Y is by itself. I'm done. My inverse function is y equals 1/4 to the x minus 3. Number 3 says y equals natural log of x plus 1. Starting with number 3, at any point, if you want to press pause and you give it a try, that would be really cool, and then you can join me on the video. Step 1 is switch x and y, so that will be x equals natural log of y plus 1. The log term is as by itself as it's going to get. This is an argument. I can't stress that enough. We cannot, under any circumstances, say, ooh, minus 1 from both sides. Nope, 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 nope. Don't ever do it. Because this is completely part of the argument. Natural log of y plus 1. If I saw like the closed parentheses and then a minus 1 on the outside, then I could add 1 or I could do something. But we can't touch that plus 1. So now I have to decide what base will I use. Again, I could technically choose any number, but being strategic, the opposite of a natural log would be base e. So I will raise up both sides using base e. E to the x will stay on this left side. E and natural log cancel, leaving behind that argument of y plus 1. Now that we've kind of unlocked y from that exponent position, we can now solve for y. My last step here to solve for y would be to subtract 1 from both sides. So I get y equals e to the x minus 1, and I'm all done. Number 4 says y equals 3 to the x plus 5 minus 9. Step 1, switch x and y. So x equals 3 to the y plus 5 minus 9. Before I can do anything, because now I'm starting with an exponential, so I know I will eventually have to take the log of both sides. So coming back up to our notes, if we're starting with an exponential and going to a logarithmic, we will take the log of both sides. Before you do that, where'd my problem go? Right here. Isolate the exponential term first. So I need to get this by itself. To do that, I can add 9 to both sides. Now that the exponential term is by itself, I'm as far as I can go with adding or subtracting, multiplying or dividing. None of those 4 operations are going to help me. But I now know that the inverse operation of an exponent is a logarithm. Now, we can take log base any number we want. But if I'm trying to get rid of 3 to a power, I'm trying to get rid of 3 being a base, I will strategically choose to take log base 3 of both sides. Log base 3 of both sides. Remember in our notes up top we said it has to be the same base. So I can't do like log base 8 and then log base 3. It has to be log base 3, log base 3. On the left, this will stay log base 3 of x plus 9. what's awesome that happens over here? Well, from those inverse properties we looked at the start of our notes, I know that log base 3 of 3 to any power will just leave behind the exponent. Log base 3 of 3 cancels, leaving behind y plus 5. Once again, you could visualize taking y plus 5 and bringing it out front from the power property, and log base 3 of 3 equals 1. So that is the mathematics that supports what we just wrote right here, because 1 times y plus 5 would literally just be y plus 5. Now that y is unlocked from that exponent position, we can finish solving for it simply by subtracting 5. Once again, you cannot do 9 minus 5. I can't stress that enough. Don't do it, don't do it. X plus 9 is the argument of this log term, log base 3 of x plus 9. So that minus 5 is simply along for the ride, and we will put it at the end. So we get y equals log base 3 of x plus 9 minus 5 as our inverse function. There's two more that we are going to look at the start of our next class. If you want to give them a try, that would be awesome. Number 5 is going to be find the inverse of y equals e to the negative x plus 7 plus 2. And number 6 will be y equals 2 times the log of x minus 8. So if you'd like to give those a try, great. Otherwise, hold off, and those will be the start of the notes for the next class. And this plus 2 kind of looks like it's a little too low, so I'll move it up. Nice job. Any questions on these notes, please don't hesitate to shoot me a question on Remind. I will see you tomorrow. Have a good night. Bye.